Okay, in this video we're going to be doing Calc AB Problem Set 118. The problems and a playlist are below. Let's check it out. Number 1, use the table above for the differentiable function f of x to answer the question. So we have f of x, we know it's differentiable. We're going to approximate f prime of 6. We've done this a lot, so we're going to start with f prime of 6 is approximately equal to. We don't want to say equal because we don't actually know. Look in the table, 6 is between 5 and 7, so we'll just use the slope of the secant line there. So f of 7 minus f of 5 over 7 minus 5, so that's going to be 3 minus 2 is 1 over 2, so 1/2. And that's it. Like, be able to do that and, in like as fast as you can. Part B, prove that f prime of x equals 3 for some x between 2 and 4. Conveniently in the table, 2 and 4 are, there's nothing in between them, so it's gotta be on that interval, like with those endpoints. So we need to show something about f prime based on f. F is differentiable. Mean value theorem is what we're going to use. So I need to establish that I can do it. F is differentiable, so f is continuous. So f of x is differentiable, which implies continuous. Now, by mean value theorem, f prime of c will be f of 4 minus f of 2 over 4 minus 2. That's 7 minus 1 is 6 over 4 minus 2 is 2. 6 over 2 is 3. So 3 for some c between 2 and 4. That's a classic mean value theorem problem. I would say that's the number one way that the mean value theorem kind of shows up on the AP exam, really. All right, the other place that it shows up is to show that the derivative is equal to 0 at some point. That shows up frequently as well. All right, next part. Part C, same table. Approximate the integral from -3 to 7 of the quantity f of x minus 2 squared with a right Riemann sum. All right, so we have f of x. We don't have f of x minus 2, and we don't have f of x minus 2 squared. I'm going to add 2 rows to my table. There's not really room, so I'm just going to start a new one here. F of x minus 2. So look at each f of x value and just subtract 2. So that's going to give us 3, -1, 5, 0, and 1. Right? We're just subtracting 2 from each of those y values. Now we're going to square them. So that'll give us 9, 1, 25, 0, and 1. Now we do our right Riemann sum based on that row of the table. So our integral will be approximately from -3 to 2 is 5. The right endpoint is +1. From 2 to 4 is 2. The right endpoint is 25. From 4 to 5 is 1. The right endpoint is 0, so that's contributing nothing. From 5 to 7 is 2. The right endpoint is 1. So we are doing... you can just leave that, by the way, on the AP exam, and you probably should. I'm going to try to simplify it. 5 plus 2 is 7, plus 50 is 57. So I'm getting 57 as my approximation, and that's how you do it. So I think adding those rows makes the problem significantly easier, and I obviously recommend it. For part D, we want to evaluate 2 to 5 f prime of x sine cubed of 3 f of x minus 1 with a calculator. Okay, so you can't just plug that into the calculator because we don't know what f of x is, but we can do a substitution to make this easier. I'm going to let u equal the thing we're doing the sine of, so 3 f of x minus 1. So that means that 1/3 du is going to be f prime of x dx. So if you look at our integral, we have an f prime of x, we have a dx, we can substitute for those. I'm going to change the bounds because I think I really need to in this case. If x is equal to 2, then u is 3 f of 2 minus 1. F of 2 is 1, so 3 minus 1 is 2. If x is equal to 5, then u is going to be 3 f of 5 minus 1. F of 5 is 2, so 3 times 2 is 6 minus 1 is 5. All right, so we can completely rewrite our integral. dx is 1/3 du. Well, f prime of x dx is 1/3 du. So we get 1/3 from 2 to 5 sine cubed of u du. Grab a calculator and do it. I got approximately -0.223. I'm not going to show the screenshot. I literally just typed in that and it just kind of went. All right, let's look at the next problem. Write a right Riemann sum that approximates the value of the integral from 2 to 7, the cube root of 3 plus 4x dx with n rectangles. Okay, so I accidentally took the limit of this thing, so I might correct this on the fly, but to do a Riemann sum, we need a delta x and that's going to be b minus a over n. So that's 7 minus 2 over n, or 5 over n. We need an x sub I, or sometimes it's called x sub k. Doesn't really matter. You just need to use some index. So x sub I for me is going to be where we start, which is 2 plus I times delta x. And delta x is 5 over n, so we get 2 plus 5i over n. So now I accidentally took the limit throughout this problem, so I actually found, I wrote a Riemann sum whose value is equal to the integral. Our Riemann sum will look like this. The limit as n approaches infinity, I goes from 1 to n, and then the sum of f of x sub I delta x, right? It's just base times height, where the height is f of x sub I, just doing rectangles. So I wrote down that the integral from 2 to 7 of the cube root of 3 plus 4x dx is equal to the limit as n approaches infinity. So to do this correctly, I guess you would say it's approximately equal to and not write the limit part. I'm just going to leave it. I think we can all deal with that. We're going to have our sum from 1 to n. The function itself is the cube root of 3 plus 4x, and I'm going to replace x with x sub I. So it's going to be the cube root of 3 plus 4 quantity, 2 plus 5i over n. And then we'll fix that. And then times delta x, which is 5 over n. So again, to correctly answer the question, I guess, as it's written, it should really be the integral is approximately, don't write the limit, and then do that. And then, for some finite n, you would be approximating it. I took the limit, so I got the exact value. I think it's okay. All right, next up. Evaluate the derivative of the integral from 5 to x to the 7th, t squared e to the cosine of t dt. So this is the second fundamental theorem. So here's our integral. What we're going to do is we're going to take the upper bound and substitute it for every t that we see. So we're going to get the quantity x to the 7th squared e to the cosine of x to the 7th times the derivative of the upper bound. So times the derivative of x to the 7th, so times 7x to the 6th. And then this cleans up a little bit, but that's it. That's the derivative. So you have x to the 14th times x to the 6th is x to the 20th, and there's a 7, so 7x to the 20th e to the cosine of x to the 7th. All right, and that's it. That's the whole problem set. I hope this was helpful, and good luck.